Hello everyone, welcome to another quick webinars by Rigaku. Today's topic will be how to improve crystal structure models by the TAAM refinement. And I just want to remind you that we will be recording this webinar and the copy will be available on the web page. Also, if you have any questions during the talk or after, just please use the Q&A button on the bottom of your Zoom call window, and we will try to answer the questions at the end of the presentation. If you are not part of our Rigaku X-ray forum, please join. If you are our customer already, please subscribe to your favorite topics and enable notifications so you can get emails if there is something interesting in the part of the forum that you want to follow. Today we have a guest speaker. Professor Paulina Dominiak is from University of Warsaw in Poland, chemistry department, where she is a leader of electron density modeling group. She graduated from the Warsaw University. She got her PhD degree in 2005 from chemistry under supervision of Professor Krzysztof Woźniak. She did her postdoc with Professor Philips Coppens in Buffalo, and then she came back to Warsaw to establish her own research group. Her main research interests are quantum crystallography and methods development for the X-ray and electron crystallography, as well as for structural chemistry and biology. Today, she will talk about the X-ray scattering model built upon the UBDB, now MATS databank and DiSCaMB software developed in her group. And now let me give control to our guest speaker and let's start the presentation. Paulina, I think you are muted.
Yes, that's what
okay.
I was searching for. Sorry for that. Good afternoon, everybody. It's a great pleasure to be here and to present you our results. Firstly, I will be talking about some scientific background regarding our methods I'm going to present to you. Then I will discuss some practical aspects of the method, show you some live examples, and then we will move to questions and answer section of this webinar. So let's start from scientific background. As you all know, X-rays are diffracted by electron density of a crystal. Therefore, if you analyze back diffraction pattern and do Fourier transformation, what you will get is electron density. However, this electron density from Fourier transformation is not easy to be interpreted, and in fact, it's not even easy to be get because we are lacking phases. We have also limits due to resolution and due to experimental errors. Therefore, during our analysis, we need to use some predetermined model of electron density, and only selected parameters of that model are refined or adjusted to experimental data. It is customary assumed that electron density of crystal can be simplified to a sum of atomic contributions. As you can see, indeed, atoms or electron densities are mostly focused on the positions of atoms. And the most commonly used model introduced 100 years ago is so-called independent atom model. That's the model which all the software, crystallographic software is using. The model assumes that atoms are spherical and do not interact. This model, in fact, is already computed using quantum chemical calculations for single atoms, isolated atoms in the ground state. And whenever you use crystallographic software, the model is applied and only position of that atoms and displacement parameters are refined against experimental data. Density is never changed. The model was very successful. We have millions of structures solved, but it does not describe entire crystal electron density. And here you clearly see on the residual map, which was computed by extracting independent atom model from total electron density of a crystal. You can clearly see maxima, the bonding positions, or lone pair positions. We call this kind of map deformation density. In fact, the effect of lacking proper description of entire electron density is seen in all data of all kinds of resolution. It's not only visible for data of sub-angstrom resolution or atomic resolution, but you can also go with lower resolution data and still have clear signal from deformation of density. Why it is so? It's because the signal comes mainly from valence electrons. And when you look at the atomic form factor, here, for example, carbon atom, and when you divide contribution to the scattering into contributions from the core electrons and contributions from the valence electrons, you can clearly see that valence electrons contribute to the scattering only at low angle diffraction. And it is therefore present in almost each data set you are collecting, because usually your data set contain low range of reflections, and then you may spend some time to have more and more data from the high resolution regime. So it's clear that we need to have more realistic model, and it is clear even more now with sophisticated software and equipment, which gives better and better data with lower and lower errors, and you very often probably see this kind of resolution maps after you do standard kind of refinement. There are many such alternative scattering models, better than independent atom model, under development now. Here you have some, the most important or the most common. And today I will focus on so-called TAAM refinement or TAAM model built from the pseudo-atom databanks. I will focus on the databank which we are developing, which is based on multipolar model. Multipolar model is a more advanced model of electron density, in which density of each electron density of each atom is described by three terms, two spherical ones, and the third one is aspherical. The model is also pre-computed by quantum chemical methods. So you here have pre-computed core and valence densities, but it has additional parameters which you can refine against your experimental data. Having more parameters to be refined means that you need to have more data to fulfill a proper ratio of parameter reflection per parameter. Usually it means that you really need to have subatomic resolution, which probably you know it's not easy to obtain for every crystal. But good thing is that these values of these parameters seems to be very similar for atoms having a similar chemical topology. Here you have an example of many molecules containing this kind of atoms and values of these parameters. So you can clearly see that they are very similar. Knowing that, next step was to build a data bank of such parameters. And currently we have three major data banks of pseudoatomic parameters. They differ a little bit by the way how they are built or from where scattering factors are taken. And I will focus today on UBDB, or better to say maths, which after we develop new software and we change a bit algorithm, we decided also to change the name. General idea of maths or UBDB is as follows. So you have many atom types in the databank. Here you have an example or examples of such atom types, for which we have parameters which describe their deformation density. And then you can rebuild back electron density of entire molecule. How the databank is built, it's based on theoretical calculations done for coordinates of single molecules extracted from Cambridge structural database. Then we are simulating experiment, but for single molecule, fit multipolar model to simulated structure factors, and we are getting molecular electron densities represented in multipolar model. And the next step, we are doing more and more nowadays statistical analysis to divide those atoms into groups of the same kind. And at the end, we have atom types which has specific for them parameters. One of the applications of databank is to use it in X-ray diffraction and to replace independent atom model. So instead of using independent atom model scattering factors, we are building electron density from UBDB. We are constructing transferable aspherical atom model and use this to compute scattering factors, more accurate scattering factors, and do refinement. And during TAAM refinement, what I want to stress, you do the same kind of refinement as in case of standard refinement. You do refine only coordinates, ADPs, and other parameters like scaling factor, for example. You don't need to refine any density parameters because they are there already taken from the data bank. So the number of parameters to be refined is the same as for independent atom model, but you are using better scattering factors. What's the effect of using better scattering factors? What's the effect after TAAM refinement? Here we have an example of a residual density maps, the one after independent atom model and after TAAM refinement. So we can clearly see that residual electron density flattens. All these densities attributed to bonding electrons are disappearing because they are now properly described by TAAM. Of course, a better model, which seems to be fitting better to the data, should give also better fitting statistics like R factor, for example. Here you have examples of TAAM and independent atom model refinements for about 80 structures, and you can see that more or less about 1% lower values are obtained from TAAM for R factor 1. But what is most spectacular, I may say, is that the geometry of molecules is changing, especially positions of hydrogen atoms. For the same set of the molecules, we have analyzed covalent bonds to hydrogen atoms. We divided them into different kind of chemical groups containing that hydrogen atoms. This analysis is analogous to what was done also for Hirshfeld Atom Refinement method. So I'm showing here results from these two methods, and on the plot you are seeing bond distances, bond lengths from independent atom model, from TAAM, from HAR, and as a reference, average neutron diffraction data are given. What can be concluded that also similarly to HAR, hydrogen atom positions improve after TAAM refinement. and they are getting quite close to neutron diffraction data. So you've seen that R factors are improving by circa 1%, that residual maps are clearing, and hydrogen atom positions are improving. There are many other tiny improvements, like precision of bond distances for any other atom types, and not only precision, but also we can show for some examples that accuracy is improving. So the method looks very, very nice, and it looks worth to be used. But over the years, what was the biggest difficulty? It was the software. So we decided to move to less specialized software, and to make it even more easy to be used. And we developed a special software library called DiSCaMB, which is designed to facilitate interface, to facilitate TAAM refinement in many kinds of refinement software already available on the world. But in the first step, we focus on OLEX2. And today I will show you how to do TAAM refinement with our software using OLEX2. To end my scientific part, just wanted to acknowledge contributions from my group. Here you see current members of my group, but also there were many other people working with me, and also people from Professor Woźniak and Professor Coppens, who started the data bank. Let's now move to practical aspects. So what do you need to do TAAM refinement? Firstly, you need to have OLEX2 software, and it is important to have 1.3 version, because the method is working only from this version. And then the two most important parts of that software is OLEX2.refine and Nosferatu. The second part is developed by OLEXsys together with Professor Zimon Grabowski group. And second piece of software, it is our program, which we call DiSCaMB TSC. And how exactly it looks like, the usage of these two softwares. So OLEX2 is performing refinement. And to tell OLEX2 that you would like to use another than independent atom model scattering factors, you need to provide a text file called TSC. The idea behind this text file is given here in this online publication. Basically, it means that OLEX2 now is able to use any kind of aspherical scattering factors, which are given to the software via this text file. DiSCaMB TSC program computes this non-spherical scattering factors within the TAAM model using MATS databank. And as an output, it is giving this TSC file. But to do so, DiSCaMB TSC needs to read a C file containing atomic coordinates and HCal file containing HCal indices for which atomic contributions to structure factors are computed by DiSCaMB TSC. How to get DiSCaMB TSC? You can go to our website. Here you have an address to that website, and just look for software and DiSCaMB TSC. and you need to fill a very short form just to register, and the software is free for non-commercial use. You will get back a link to download a zipped folder in which you have many kind of informations and examples, but the most important part of that is the program itself. Once you have a program, you should copy that program to the folder in which you have CIF and HKL files for your crystal structure for which you would like to perform TAAM refinement. Then the only thing what you need to do is simply double click on that file. And the file is executed, the program is executed, it is computing scattering factors on the basis of the structure here, and it's printing out scattering factors in TSC file. In addition, it's printing some kind of log file, and the most important information that in that log file for you is information if all atoms were, or all atom types were recognized in your molecule. Here we have a molecule containing 9 atoms, and all of them were recognized. And atom types for them were found in MATS databank. After you generate TSC file, you just need to execute OLEX2. Once again, it's important to have 1.3 version of OLEX2. Go to work to refine, and next, what is important, you need to use OLEX2.refine for refinement. This entire procedure, the TAAM refinement, only works with OLEX2.refine. It will not work with ShellXL, for example. And then you do the usual refinement. Here you have an example how it looks like after the refinement. Here you have very little information that tabulated atomic form factors were used for the refinement. And what you should see at the first glimpse after you do this kind of refinement, you should see that R factors lowers, that bond distance, bond length increases, and you also should see improved residual maps. Here you have an example how these values looks like for independent atom model refinement, and then for TAAM refinement. And how residual maps differs between independent atom model and TAAM refinement. You can clearly see that all these residual densities at bonds are disappearing, and the map is much flattened. To summarize, I would like to emphasize that this is still kind of alpha version. You need to manually execute the program. It's not integrated fully yet with the OLEX graphical interface. The work is in progress, and in collaboration with OLEXsys and Professor Szymon Grabowski, it will be available within a couple of months. Another part or piece of work missing is that the CIF file which is generated, it contains proper information about geometry, coordinates, statistics, but the information about atomic scattering factors is not updated, so just be aware of that. And to look at Fourier maps, you need to use FCF file. Only this file contains proper scattering factors computed from TAAM model. The databank at the moment contains more than 300, probably, well, we are approaching 400 now, atom types for light elements. like carbon, hydrogen, nitrogen, oxygen, and so on. It does not contain heavier elements yet, and whenever the structure contains heavier element, a spherical model is applied to that particular atom. Also, if there is no atom type for specific light element, atom type then spherical model is applied. So you can still do refinement, but some atoms are having spherical model applied. We also do not treat properly yet disordered molecules or organic or metallic molecules. The work is in progress. Let's move now to some live examples. I will switch now to show you my desktop. I prepared several examples. Most of them are downloaded from some scientific journals from this year, or yeah, basically all of them are from this year. The first example is a kind of a textbook example of how it should look like. So here you have a crystal structure refined using standard independent atom model. You have quite good, you can see that these data are really very good. And also already R factor is quite small. But residual maps have a specific feature, specific for independent atom model. You have positive values at the bonding region and a bit of positive values of electron or excess of electron density around oxygen atom here, for example. Here you have what happens after you do a TAAM refinement. Maps are visibly clearer. I'm using exactly the same contour level, but also I will move a bit these two windows just to show you how the statistics are changing. So you have more than 1% point less in terms of R1 factor. You are getting well, slightly better flak parameter, better goof factor. And to show you how the speed of refinement compares between independent atom model and TAAM, I will just run now 10 cycles of independent atom model refinement. So you will see how long it takes here. So it's basically done now. And here you have TAAM refinement, also 10 cycles. Yeah, okay, maybe it's not really, here you see that after one cycle everything converged, so maybe that was a bit faster. I have another example in which it's much clearer. But what I wanted to stress is that TAAM refinement is in speed very comparable to independent atom model. You may not like that it's twice slower, but it's still seconds. Maybe minutes, but not hours. Another example, let me move here, yes, very nice data set, beautiful residual density showing bonding density. And this is after independent atom model. And now the same structure refined with TAAM. model map, residual map is much clearer, and some features appears. Here probably you have traces of very small disorder, which was not really visible after independent atom model refinement. And still we have some signal around bromine atom, which might indicate some other effects like absorption correction, anharmonic motion, as well as you cannot exclude that our modeling is not 100% perfect. Another example, this time we'll have two molecules in asymmetric unit. And after TAM, the map is really clear. And here I would like to show you how long does it take to compute TSC file, how long does it take to run DiSCaMB to be ready for TAM refinement. Let me now find a folder containing this particular structure, 14. So this was yeah, so that's the one. So as I told you, it's enough to just double click on our software and to have in the folder CIF an HKL file. So now it's computing and it's done. And you have a new TSC file and new log file for this structure computed. And we can go to the log file. And here it is written that the structure contains 60 atoms and all atoms were recognized. So it is really fast. And some even bigger structures, 4 molecules in a symmetric unit, a bit high error factor, higher than 5%, but seems that these are very good data because we are clearly seeing residual densities at bonding regions. And after TAM refinement, what you are getting error factor 3.5%. So it's much lower than 5%. Clear residual density and some traces of some disorder close to one of the molecules. Yet another example from copper radiation. Moderate quality data. You can see here. And after TAM refinement, statistics are getting better. Now we are below 5%, magic 5%. Maps are different, but still there is something going on in the data. These are not very clear residual maps. Maybe this is some indication that you should go back to integration software, or also RINT is indicating that. So this is an example where you can remove bias from your scattering model, and then you may more clearly see if you have problems resulting from some other phenomena. And at the end, I am showing you an example where two atoms were not recognized in our data bank. So this is independent atom model refinement. And TAAM refinement. And already from the residual density, you can clearly see that these two atoms were not recognized, and spherical scattering model was used for these two atoms. But still, the rest were recognized, properly modeled. So overall, R factor is lowering. Yes, so that's all from my side. And now I'm ready for your questions.
Thank you, Paulina. We have a few questions. Let's start with the one that we group a few questions together. There is a question, what's the minimum data resolution needed to be applied for such a refinement? And how low resolution data set can be used with your type of refinement, and what radiation can be used? So I think you answered some of those questions showing the examples, but maybe you can sum up those in one answer.
So there is no dependence on radiation. So any kind of radiation can be used. With resolution, so this is something which is from the, at the beginning not according to your intuition. The worse the resolution, the better results you will get using TAAM. So basically, we have checked it with 1.2 angstrom resolution for small molecules, and it was still working much better than independent atom model. I would say that especially if you have if you have worse resolution, if you have very bad resolution, especially then you should use TAAM model, because the lower resolution you have, the stronger signal from valence electrons is in your data comparing to core electrons.
Okay.
Yes, so that's basically, I think, everything.
Thank you. So we have also a question that I can summarize, that this method works mostly for organic crystallography, but is it possible for use, for example, for the mineral crystallography?
So in theory, it could be done. In practice, our data bank is, yes, built only for organic molecules. So we don't have any atom types which are common in inorganic structures, purely inorganic structures. Another issue is that these are mostly heavier elements. With that, we are seeing some difficulties in using a multipolar model to describe them properly. And nobody never checked how transferable this kind of densities are for inorganic fragments.
Thank you. And let's then go to the other question. Could you please explain what are the advantages or disadvantages of the TAAM refinement compared to the HAR refinement from Grabowski group?
Mm-hmm. So these are similar kind of methods. Both are providing aspherical scattering factors. I would say that TAAM is somewhere in between independent atom model and Hirshfeld Atom Refinement. Well, it's much closer to Hirshfeld Atom Refinement than to independent atom model. It's a bit simpler than Hirshfeld Atom Refinement than HAR, because the density is built from the data bank. So it is not exactly density computed for that particular molecule. So it may differ a bit. Our data bank is not taking into account intermolecular interactions. So these are negative sides of the TAAM when you compare it to HAR. On the positive side, you saw the speed. TAAM is almost as fast as independent atom model. For HAR, you need to spend more time to compute your scattering factors and basically to compute scattering factors. Refinement after it will be moved to OLEX will take the same time.
Mm-hmm. Thank you. And we have also a few questions. Let's select one. Is it possible to refine hydrogen atoms anisotropically? Would you recommend or discourage for it? I'm guessing that it could, in your method of TAAM refinement.
Yes, it is possible. I was not showing it here, actually, but yes, we did check it. It seems to work. It seems to work similarly, like in case of HAR. So you are getting slightly better positions. ADPs are more or less okay, but usually not as good as from neutron diffraction. What I wanted to show you is how it really looks like now. Here, just for this one particular example. So this is up to the user to decide whether he or she wants to go to this direction, and needs to be careful. Some ADPs are getting non-positive defined. I did something wrong, sorry.
I think you have to switch in OLEX the view to display.
Yes, it might be so, right.
But the answer is yes, it's possible. If the data is good enough, then you should be able to refine it.
Yes.
So we have a question under the invariant approach has been employed to refine the ligand, and subsequently it was possible to determine that the central metal atom type. Can this be useful application for TAAM?
Yes, we were thinking about that as well. So we do not have metal centers, and probably will not have it in near future. But yes, similarly, you can parameterize your ligands. At the moment, it's not very properly done because at the moment we are still recognizing that there is some kind of bonding between metal and ligand. So the first atom from the ligand will also not be recognized from the data bank. So this, but this will be probably in near future corrected. So yes, you can select just the ligand and parameterize it, run TAAM refinement, and it should give you similar results as Birger have shown for invariant.
Great, thank you. And maybe the last question, is there any easy way to use these results for the atom in molecule analysis?
Not really, and probably not in the near future in case of TAAM refinement. What must be stressed that you cannot really perform ketam analysis on Fourier densities because they are still just Fourier densities having Fourier truncation errors. So you cannot analyze them directly to get quantitative numbers. To do so, you would need to analyze TAAM model in itself. You need to start from multipolar model. And this is not possible in OLEX. One solution would be that our software will print out a special file containing all the parameterization, and then the user would need to switch to some more sophisticated program like XD or MoPro to do Qt analysis. Jakub, I'm not hearing you.
So that was our last question. Thank you for joining the TOPIQ webinar. I want to remind you that we can continue discussion on our forum, and also if you keep your Chrysalis Pro package updated, I just want to remind you that the OLEX that is included inside should be already version 1.3. So what you only need to start your TAAM refinement is basically to download the small program from the webpage that Paulina showed us during talk. So if you have any problems or results that you want to discuss, again, let's meet on our forum. Thank you again. We'll stop the webinar now.
Thank you very much.
Thank you.